A value for the volume of a regular tetrahedron can be found using this sum, and we'll look to show in this video why this sum can be used. Our first step is to think of a regular tetrahedron inside a standard cube. Inside this cube we have a volume of space taken up by the tetrahedron, but we also have some empty space. There is, in fact, 4 equal-sized sections of empty space inside the cube and around the tetrahedron. There's one here, another here, and there's actually a 4th. Same size, can't see it from this angle, but it's just behind this side of the tetrahedron. So, what we have is the volume of the cube itself, but also the empty space volume that is not the volume of the tetrahedron. And this leads us to see the following, which is that the cube volume minus the volume of empty space will leave the result that is the tetrahedron volume. So, working out the volume of the cube and the volume of the empty space will lead to us finding out the volume of the regular tetrahedron. And firstly, for the cube volume, the volume of the cube is just an edge length cubed. So we have A cubed. But we're looking for a final sum that will be in terms of an edge length of the tetrahedron, S. So, instead of A cubed, we would like an expression in terms of S. And we can do this if we focus on one of the faces of the cube with the regular tetrahedron inside. Now, the face of the cube is a square, and the edge of a tetrahedron is a diagonal of the square face. And when we have a square and the diagonal length is given by root 2 multiplied by the edge length of the square, and this leads to an expression for A, which is S over root 2. So, for our cube volume, A cubed can actually be written as S over root 2 cubed. And when we cube S over root 2, the result is S cubed over 2 root 2. So now, what about the volume of the empty space? Well, each section of empty space is a triangular base pyramid of the same size, and the volume of a triangular base pyramid is given by 1/3 multiplied by the base area multiplied by the height. And as we have 4 of these pyramids, we multiply this value by 4. Now the height value is quite straightforward. It's just the height of the cube itself, which in terms of S we worked out to be S over root 2. Now the base area of one of the sections of empty space is just half of the base of the actual cube. The base of the cube is S over root 2 squared, and half of that we just multiply by a half. And when we multiply this out, the result is S squared over 4. So now we can proceed to work out the volume of empty space. So we have our third, our base area, squared over 4, our height is over root 2, and this is all multiplied by 4. And when we multiply these terms all together, we get 4s cubed on top and 12 root 2 below, as 3 times 4 is 12, and we still have the root 2. And this can actually be simplified a bit further as a fraction to s cubed over 3 root 2, as 4 over 12 can be written as 1 over 3. So, cube volume minus empty space volume gives us s cubed over 2 root 2 minus s cubed over 3 root 2. However, we would like to have the same denominator. If we multiply here by 3 over 3, doesn't change the overall value, and over here multiply by 2 over 2, which again doesn't change the overall value, this will give us 3s cubed over 6 root 2 minus 2s cubed over 6 root 2. So now we can carry out this subtraction. 3s cubed minus 2s cubed on top gives us s cubed, and we have our denominator of 6 root 2, which we notice is the volume sum that we stated at the start. And with the help of looking at a regular tetrahedron inside a standard cube, we've seen why this sum can be used to obtain a value for the volume of a regular tetrahedron.